Calculus, Section 5 of Chapter 2, Continuity. I'm your host, Dr. D. Let's get started on this. First thing, you may be wondering why we skipped Chapter 4. Well, Chapter 4 is basically a strict definition of limit theory, and it basically says that the limit at a particular x value exists if for any range of x values, epsilon, you can find a corresponding range of y values, delta. And you do these proofs to confirm that, and it has absolutely nothing to do with anything with application. And so then the second reason we're skipping it is because it's not included on the AP exam. So that means we don't need it.
That's the smartest thing I've ever heard anyone say about anything.
Okay, so cruising onward to Section 5, Continuity. Now, in the past we've defined continuity as if you can draw the function without lifting up your pen, then it's continuous. And we talked about discontinuity being point discontinuity, which would mean only one point is discontinuous, but the whole rest of the function is continuous. Infinite discontinuity, which means you've got a vertical asymptote, so like f of x equals 1 over x is going to be discontinuous at x equals 0 because you have a vertical asymptote, and that's infinite discontinuity. And then you have jump discontinuity, like a step function. There's a discontinuity at each step. So this section, though, is going to more firmly define continuity according to limits. And you need to memorize it. Memorize it? Okay, shut up. Okay. Yes, you need to memorize it. Why? Well, for the same reason we're skipping Section 4. We skip Section 4 because it's not on the AP exam. We're memorizing the definition of continuity because it is on the AP exam. Okay, so here we go. A function f is continuous at some x value a if and only if, I didn't just misspell the word if here, the limit as x approaches a of f of x equals f of a. Now, that seems simple, but really it has three separate requirements, and we need to understand each separate requirement. And do you think there could possibly be some sort of way that I could determine if you actually know this stuff? Like, you think this stuff might possibly occur on a quiz? Yes, it might. Okay. So, be ready for that. All right, so a function's continuous at some x value if the limit as x approaches a of f of x equals fa. Now, that's really saying three separate things. First of all, f of a must be defined. In other words, a has to be in the domain of f, or else you can't have the limit as x approaches a of f of x equals fa if fa doesn't even exist. So f of a must be defined, or a must be an x value that's in the domain of the function f. Okay, cruising onward. Next thing, the limit as x approaches a of f of x must exist. Well, what do we mean the limit must exist? That means the left-hand limit must equal the right-hand limit for that limit to exist. Okay, so a has to be in the domain of f. The limit as x approaches a of f of x must exist. And then finally, those two things have to equal each other. Okay, now, let's look at 3 situations where we have discontinuity because one or more of these are violated. Okay. Okay, so here are 3 things. F of a is defined, limit as f of x, or limit as x approaches a of f of x exists, and the limit as x approaches a of f of x has to equal f of a. All right, now we've got 3 points of discontinuity. So this first point at x equals -6, is f of a defined here? No, it's not. So since f of a is not defined, then that means this function is discontinuous at x equals -6. Now, let's go on. At this point, does the limit as x approaches a of f of x exist? Yes, it does, because the left-hand limit ends up equaling 1, and the right-hand limit equals 1. So, point number 2, the limit does exist, but the fact that f of a is not defined means it's disqualified. And then clearly, number 3 can't be true if f of a doesn't even exist. Okay, so next point of discontinuity, we have jump discontinuity here. And so let's see which one of these rules is violated. Does f of a define? Is f of a defined? Yes, it is. F of -2 equals -1/2. So f of a is defined. Well, then does the limit as x approaches a of f of x exist? So, in other words, does the limit as x approaches -2 exist? Well, the left-hand limit ends up equaling -1/2, and the right-hand limit ends up equaling 2. So, clearly, the limit does not exist. Oh, it's blue again. How embarrassing. There we are. Okay, so the f of a is defined, but the limit as x approaches a of f of x does not exist. So clearly, number 3 is invalid, because if the limit doesn't exist, then it can't equal anything. All right, now on to the third discontinuity, and that is at x equals 4. Okay, now, does f of a, or is f of a defined? Yes, it is. F of a, f of 4 equals 3. So f of a is clearly defined. Now, does the limit as x approaches a of f of x exist? Does the limit as x approaches 4 of f of x exist? Well, the left-hand limit equals 1, the right-hand limit equals 1. So, yes, the limit exists. So the function is defined here, and the limit exists. But the third situation, the limit equals 1, and f of 4 equals 3. 1 does not equal 3, so this is disqualified. on the basis that the limit as x approaches a of f of x does not equal f of a. Okay, so what we've seen here is if any one of these three things is violated, you don't have continuity. So with point discontinuity, what's violated is f of a is not defined. Also with infinite discontinuity, f of a would not be defined. Then with jump discontinuity, f of a is defined, but the limit does not exist. And then with the removable discontinuity, basically you have a point discontinuity with another point defined. So you see that f of 4 is defined, and the limit as x approaches 4 of f of x exists, but they're not equal to each other. So you don't have continuity at x equals 4. So that's it. Now, this is what I told you. You need to memorize all three things, because notice, if you only understand one thing, then you're not going to understand all of the intricacies of the exceptions. Okay, cruising onward. Okay, so like I said, continuity, this isn't an application type thing. We're not going to find engineering type problems with continuity, but you definitely need to understand it because it's a mathematical principle. And like I've been telling you for years, math is all about mental weightlifting, and this is a serious weight to be able to lift. All right, so let's check out page 125, example 2. All right. Where are each of the following functions discontinuous? Okay, so we have f of x equals x squared minus x minus 2 over x minus 2. So clearly this is discontinuous at x equals 2, because that would make the bottom 0. Now I don't care what it makes the top, the fact that it makes the bottom 0, it's discontinuous. So basically what we're saying is at x equals 2, the function is not defined, so f of 2 does not exist. Okay, now, example B, f of x equals 1 over x squared if x does not equal 0, or it equals 1 if x equals 0. Okay, now where is this discontinuous? Well, notice we don't have the same problem as we had over there. At x equals 1, this is perfectly well defined. It equals 1. And anywhere else, it's perfectly well defined. It's 1 over x squared, and x squared is going to be, or 1 over x squared will be continuous as long as x does not equal 0. But the problem here is the point of discontinuity is at x equals 0. Why? Because, remember, the limit as x approaches 0 of f of x must equal f of a. Well, what's the limit as x approaches 0 of f of x? It's, as I approach 0, let's just look at this graph, 1 over x squared. As I make x a smaller and smaller number, both from the left and the right, the limit is going to equal infinity. So basically, the limit as x approaches 0 of f of x equals infinity. Now, what is f of, oh, you know what, I put a there. We're not talking a anymore. We're talking a already is 0. Okay, so what is f of 0? Well, if x is 0, f is 1. Unfortunately, infinity does not equal 1. Does not equal 1. We'll edit that out later. Okay, so basically we've got the point of discontinuity at x equals 0 there. Is that what the book says? Oh yeah, it's what the book says. Okay, that's happy. Okay, then example C. Yeah, we'll just stick with blue here. All right, so we've got f of x equals x squared minus x minus 2 over x minus 2. And that is if x does not equal negative 2, or if x does not equal 2, I mean. And then equals 1 if x does equal 2. All right, is that continuous? Okay, well, let's do all our 3 points. Does f of 2 exist? Yes, it does. F of 2 equals 1. What's the limit as x approaches 2 of this thing? Well, the limit as x approaches 2 of x squared minus x, minus x, minus 2 over x minus 2 equals the limit as x approaches 2 of, can we factor this thing? Well, multiplies to get negative 2, that adds to get negative 1. It's x plus 1 and x minus 2. Is that right? Yeah, that's right. It's right. Okay, so this equals the limit as x approaches 2 of just x plus 1, which would equal 2 plus 1, which is 3. Okay, well that's happy. Now, we found out that f of 2 exists. Point 1. The limit as x approaches 2 exists. That's 2. But the limit as x approaches 2 of f of x has to equal f of 2. Well, we just found out that limit equals 3 and f of 2 equals 1. So, since 3 does not equal 1, we have discontinuity once again. And if you look at the bottom, you'll see the graphs of these. Example A is just a hole there. It's just not defined at x equals 2. Example B, you have infinite discontinuity, so even though the function is defined at x equals 0, there's no way that that's continuous. And example C, you see that the hole doesn't match up with the point. Now, how could we fix this so that it would be continuous? Well, the way we fix it is to let this point plug up the hole. So if we were to put 3 here, so f of x equals 3 if x equals 2, now it's continuous because 3 equals 3. So as long as we plug up the hole, in other words, we define f of x to equal 3 when x equals 2, because the limit as x approaches 2 of f of x equals 3, then we've got continuity. So that's why that's called removable discontinuity, because I can remove the discontinuity simply by defining the one value that it's discontinuous, and now the discontinuity has been removed. Okay, And the last one is our step function, which you can see. We're not going to take time on that. We talked about that yesterday, or in section 3. It's not continuous because at any given integer, the left-hand limit and the right-hand limit don't agree. So the limit doesn't exist, so that means we have discontinuity. And they're asking if it's continuous at... they're asking where it's discontinuous. So it's discontinuous at all integers. And that's it. Okay. Cruising onward. We've got a bunch of properties here now, theorems and properties that are really pretty self-explanatory. Definition 2, we've been talking about that forever. I'm sorry, this isn't the definition of limit. It's, okay, a function's continuous from the right at some x value a if the limit as x approaches a from the right of fx equals f of a. So if we take, let's just look at an example here. Okay, if we take the function y equals 1 over x, well, clearly that's not continuous at x equals 0. Oops. Okay. There's my function. Now, this is only discontinuous at x equals 0. So what we could say is it's continuous from the right of x equals 0, and it's continuous from the left of x equals 0. But it's just not continuous at x equals 0. So if I said the limit as x approaches a from the right, well, let's just go. The limit as x approaches 0 from the right of f of x will equal f of, oh, you know what, we don't want to use 0 here. We want to use, yeah, let's just use a. Limit as x approaches a from the right of f of x equals f of a. That means it's continuous from the right. Now what does that mean? Well, if I take x equals 5, now the limit as x approaches 5 is the left and the right hand limits agree, f of 5 exists, and they're equal to each other. Basically, the limit of everything to the right of 0 of f of x will be continuous. Then, same thing. The limit of everything left of a so this is continuous to the right, and this is continuous to the left. Okay. A step function would be the same thing. It's going to be continuous to the left of the discontinuity and continuous to the right of the discontinuity. Now, take a look at top page 127. Theorem 4. If f and g are continuous at some x value a, and c is a constant, then the following functions are also continuous at a. The sum of the functions. So if I add f and g, I've got continuity everywhere. If I subtract f and g, I've got continuity everywhere. If I multiply f by some constant, then I have continuity everywhere. If I multiply f and g, I have continuity everywhere. And if I divide f by g, I've got continuity as long as g doesn't equal 0 at the given point we're interested in, a. Now, notice it's going to do the proofs of these, which you're using the limit laws to prove them. I would say it's actually easier to see the rationale of this just intuitively. If we have some function f and some function g, so here's f, here's g. Yeah, it totally doesn't matter. Now, notice, at any given x value, I can add these y values and I will get another y value. Which means, at every x value, the sum of these two functions will also be defined. There's no discontinuity in anywhere from a to b, so that means any point I pick, if I add the two functions, they're defined. If I subtract the two functions, I'm going to have a value, because any point I pick, if I subtract a from b, or f of a from g of a, then I'm going to end up with some real value, because f of a is real and g of a is real, so when I subtract them, I get real. So it really has to do with the closure property. If I take any real value and multiply them, I have a real value. If I take any real value and multiply by a constant, I have a real value. Now the only catch is going to be if I divide, if f or g equals 0, if I divide, well, right here, where f is 0, and when I divide g by f, then I'm going to have undefined. So that's the only case where you're not going to have continuity, is if the denominator equals 0. Okay, look at theorem number 5. Any polynomial is continuous everywhere. That is, continuous on the set of all real numbers from negative infinity to positive infinity. So that really seems self-evident too, because a polynomial function is going to go up and down and up and down, and it's going to have one less term than the degree. And so we know all polynomial functions are continuous, from a straight line to, what is this? 1, 2, 3, 4, with all these, that's kind of weird. Okay, it's continuous everywhere because you're just going to have terms, but there's not going to be any breaks. Then, any rational function is continuous everywhere that it's defined. Okay? That's an interesting little caveat. A rational function would be like f of x equals 1 over x. Rational ratio. Okay, so is this continuous everywhere that it's defined? Well, yeah, because, nice, okay. This is continuous everywhere that it's defined. Where is it discontinuous at x equals 0? Well, it's not defined there, so it doesn't matter. So basically, any rational function is going to be continuous everywhere that you don't have your vertical asymptote. So whatever x value makes the denominator 0 is discontinuous, but that doesn't count because that's not in the domain of the function to begin with. So rational functions are continuous everywhere that they're not undefined. And that's really the same as, notice on page 129, the trig functions, the root functions, square roots, cube roots, fourth roots, those are going to be continuous everywhere that they're defined. Trig functions, well, you look at the sine and cosine, well, clearly they're continuous everywhere. But tangent has those asymptotes. So tangent is at pi over 2, let's see, we're making pi over 2 every 2. So pi, 3 pi over 2, negative pi over 2. Okay, so here's what tangent curves look like. Just refreshing your memory. Okay, so your tangent curve is going to look like this, and like this, and like that, and like that. And it's just going to keep on going forever and ever. Hallelujah. Okay, so is this continuous everywhere in its domain? Well, yeah. Like if we look at the domain, basically one of these curves, it's continuous from the asymptote to the asymptote. It's not continuous at the asymptotes, but at those asymptotes, the function isn't defined. So a trig function is going to be continuous everywhere that it's defined, everywhere that it's in its domain. And same thing with exponential functions. Well, exponential functions are continuous from negative infinity to positive infinity. But logarithmic functions, you can't take the log of a negative number. Well, that's not defined in its domain, so it's continuous everywhere that it's defined in its domain. Inverse trig functions, same thing. It's only continuous in its domain, but so you're going to have in inverse tangent, you're going to have little points of discontinuity, but those aren't defined in their domain. Okay, let's get out of this now. So theorem 8 says if f, oh, you know what, before we cruise on, take a look at example 6. Where is the function f of x continuous? Well, it's going to be continuous on its domain. But what's its domain? Well, natural log x has to be positive. Inverse tangent x, x has to be between, oh wait, no, I'm sorry. Inverse tangent x is continuous everywhere. And then x squared minus 1 is continuous everywhere. So basically this is continuous from, oh no it isn't. X squared minus 1 is continuous everywhere, but it's on the denominator, so it can't be 0. So at x equals 1 would make it discontinuous. So we can say the function is continuous from 0 to 1, and then it's continuous again from 1 to infinity. It's not continuous at 1 itself, because you have 0 in the denominator. It's not continuous at any negative x value, because you can't take the natural log of a negative number. But it's continuous everywhere else. So that's happy. All right. Yeah, theorem 8 is just common sense too. If f is continuous at some point b, and the limit as x approaches a of g of x equals b, then the limit as x approaches a of f of g of x equals f of b, because of the definition of continuity. You can substitute the limit as x approaches a of g of x for b. That's all they're doing. Theorem number 9, if g is continuous at a and f is continuous at g of a, then the composite f of g is continuous at a. All right, that's basically a substitution too. You can look over that proof, but it's pretty standard too. So now we're going to the second thing in this lesson that's absolutely super important. So the first thing you might remember is the 3 qualifications for continuity, which are super important. The second thing that's super important is called the intermediate value theorem. And you've already worked with it before, you just haven't had it stated as such. So here's the intermediate value theorem. Suppose f, that's like math proof language, suppose f is continuous on the closed interval a to b. Now, a closed interval is symbolized with brackets, and what it means is a is included and b is included. The open interval is characterized with parentheses instead of brackets, and open intervals, a is not included and b is not included. So now, when you see an interval with infinity in it, like from 0 to infinity, well, you'd have to have infinity with a parenthesis because there is no such value as infinity. So you're never going to have infinity with a bracket or negative infinity with a bracket. They're always going to be parentheses. Okay, so back to the range. We're supposing that we've got a function that's continuous on some closed interval a to b. So everything from a to b, including a and b, is continuous. And let n be any y value between f of a and f of b, where f of a does not equal f of b. Okay, if we satisfy those, this is basically the hypothesis here, everything from suppose to the period. Then, the conclusion, there exists an x value, we're going to call it c, in the open interval from a to b, such that f of c equals n. All right, I know that's really confusing, but let's look at it. Here's our function. This blue curve is our function f. And f is continuous on the closed interval from a to b. In other words, from a to b, there's no discontinuity. Now, n is any y value between f of a and f of b. And notice f of a and f of b have to be different. In other words, we have to go from some point to some other point. So we either have to go up or we have to go down, but f of a and f of b can't be on the same level. That means now there is some value in between them, and we're calling it n. So that's what we have, is we've got a continuous function from a to b, and then we've got some y value that we're calling n in between a and b. So what our theorem says, there exists an x value that we're going to call c in the open interval from a to b, such that f of c equals n. Where's that x value? Find c here. Well, what we do is we say, okay, if n is here, then that means C has to be here. See, what does that mean? That means that f of C equals n. All right, what's this saying in plain language? What it's saying is, if I'm going from A to B with no breaks in it, and the point at A and the point at B have to have a change in altitude. I have to go from one point in the y to another point in the y. Now, what that means is, I'm going to have to cross through this level. If I'm going to change levels from f of A to f of B, then I have to go through n. And if I have to go through n, that's a y value n, there has to be an x value that associates with that, because there's no break here. Now let's say if I had discontinuity here, like let's say this was discontinuous right here. Well, now there is no x value, because the n value hits the hole, and there is no x value that corresponds with it. Well, if it's not continuous, then the whole theorem is out the window, because it says it has to be continuous. But if it is continuous, then there's guaranteed to be some x value associating with that y value. All right, let's go over here. Where is my C value here? Well, basically, it's all the x values on the level of the n. So, there's one, there's another. Oh, made it a solid line, how embarrassing. And there's the last one. So we have C sub 1, C sub 2, and C sub 3. All this is saying is, if I go from low to high, I have to cross through every point in between. And this is what we did last year when we were looking for zeros. Remember, we're looking for the integer in between which there's a zero. So let me just show you that example. We're looking for zeros, and we find out that f of negative 1 equals negative 3. And, let's not use negative 1. I don't want to confuse you with a y value that's 0. Okay, so let's say f of 1 is negative 1. And f of 2 is 1. Oh, come on. All right. Now what we said last year was there has to be a root in between x equals 1 and x equals 2. See, this is your A, and this is your B. And so this is your f of B, and this is your f of A. Now what's my n value? It's the x-axis. Why? Because we're interested in where the function crosses the x-axis. So we're interested in n being x equals 0. And what are we looking for? Well, we know if this thing's continuous, somewhere it might sneak up here and then fake us out and sneak up again. Somewhere it has to cross over if it's going to get from that point to that point. That's what the intermediate value theorem is saying, is if I've got 2 points and I've got a continuous function so there's no gap in between there, then I have to cross over the point n. And most of the time the point n we're interested in is the x-axis, but it could be anywhere. So that's what it's saying. Let's check it out one more time. Suppose f is a continuous function on the closed interval from a to b. And let n be any y value in between f of a and f of b, which, like we said, is a lot of times where y equals 0, because we're looking for zeros. And f of a cannot equal f of b, because it's got to travel upward or downward. Then there has to be